Hi everyone, welcome to Om Learning Lab. Today we are going to look at a problem which wears multiple hats. On one hand, this is the kind of a problem which can appear in pure mathematics examinations, while on the other, this is also the kind of a problem which can be posed as a puzzle or a programming challenge with slight modifications in coding interviews. Especially, this can be asked for machine learning based roles, which I can vouch for from personal experience. Now, originally this question was asked in INMO 2015. In order to appreciate the real beauty this problem possesses and the learning that we can get from it, we'll be solving it in two parts. In the first part, we will be solving it using pure mathematics approach to build the intuition around the problem, to get a flavor of the problem. In the second part, we'll try to generalize the problem and we'll build a more robust solution for the problem using bottom-up DP, dynamic programming. And in fact, we'll write a code and we'll see it live in action. So, without any further ado, let's get started. Now to begin with, let's just give a brief reading of the problem. So, they are saying that there are 4 basketball players A, B, C, D, and initially A has a ball. So we have A here, A has the ball, and the ball is always passed from one person to a different person. So self passes are not allowed. So this line basically means that self passes are not allowed. So A cannot pass the ball back to himself. In how many ways can the ball come back to A after 7 passes? Okay, and they have given a couple of examples here as well. So here, let me just clean this up a little bit. Okay, so here this just means that self passes are not allowed. And here this is an example that they have given, that A is passing to C, C passes to B, so on and so forth. And every consecutive pair is different. That's the rule that they have mentioned. And okay, so they have given 2 examples and they just want that if there are 7 passes, how many total ways are there? Now, if we think about it, what can happen? So, if there are 7 passes, if there are, let's say there is a single pass. If there is a single pass, we basically have 2 positions to fill. And here we can have B, C or D. It definitely cannot be A. So, because self pass is not allowed. That has been established. So, if there were a couple of passes, here there can be something, and here it has to come back to A. So there will be 3 people. Similarly, so on and so forth, since there are 7 passes, there will be in total 8 positions for us to fill. So the first one has to be A. The last one has to be A. In between, there will be 6 positions, right? So let's call them X1, X2, X3, X4, X5, and X6. So we have the first pass, we have the second pass, we have the third pass, fourth pass, fifth pass, sixth pass, and the final pass. Now, if we observe carefully, this X1 can never be A. That has been clearly mentioned in the problem, that a pass has to go to a different person. So this cannot be A. So this X1 cannot be A. It can be B, C, or D. Similarly, since at last it has to go back to A, it cannot go back from A to A. So X6 also cannot be A. So it can be B, C, or D. Right. Now, if that is so, where can we place A? If let's say I wanted to think about where can I place A? Because if you think about it, B, C, D can be placed in between. There is no such restriction on B, C, D as there is on A, because we have to pass it to a different person. Now, where can I place A? Can I place A here? Of course, I can place A here. But if I place A here, I cannot place A here. So let me represent that with some different color. Let's talk about placement of A in green color for the time being. Just a second. Let's talk about placement of A with green color. So if I place A in X2, I cannot place A in X3. Similarly, if I place A anywhere in X, if let's say I place A in X4, I cannot place A in X5. So in this scenario, I can place A only in two positions. Let me just keep this for the time because we'll have to erase it multiple times. So in the first case, if I place A in X2 and X4, only two times I can place A from the given 6 positions. Now let's say I say that I don't want to place A in X4. Let's say I want to put A in X5. Similarly, if I put A in X5, again X6, obviously we cannot put A. In X4 also we cannot put A, and X3 is also blocked. So again, we have only two positions where you can place A. In fact, if we think about it, anywhere from these 6 positions, if we pick any two positions at random and we place a couple of A's over there, they will automatically block 4 positions. Why is that so? Let's say we have 3, 4, 5, 6. We pick any two positions in between. Let's say we pick this position, and let's say we pick this position. This blocks these two positions for A. This A will block these two positions. And originally, of course, here we cannot place A to begin with, right? Because it has to start from A and it ends from A, and self passes are not allowed. So regardless of from these 4 available positions for A, wherever you put the couple of A's, you cannot put any more A. That is the idea that I'm trying to convey here, because we have 4 positions, we have to place A's, we have to put them in a separated fashion. Regardless of what you do, maximum we can place 2 A's. Just to elaborate that a little further, if we have 4 positions in between, so X2, X3, X4 and X5 are available for A, I can put A here and here, this is one arrangement, or A here and the other A is here, this is another arrangement, or the first A is in the second position, the second A will be in the last position. This is one arrangement, and this is the only possibility because self passes are not allowed. So we only have 3 possibilities to put A. And maximum times we can place A is 2. Now this helps me a lot. So the simple observation that there is a restriction on A helps me to solve this problem easily. Because now that I have understood that I can at the most place A 2 times under any circumstance, I know there can be just 3 cases to this problem. What are the cases? So the cases will be that either I have 2 A's in between in the 6 positions, in fact in the 4 positions that's specific for A, or I have just 1 A, or I have no A. These are the 3 cases, and we can study these cases separately and build a complete solution. So for the first case, let's say we have 2A, case 1. We have case 1, we have 2A, case 1, 2A. What will happen here? So we start with A, we end with A. In between we have 6 positions. And I am saying that I want to put 2 A's somewhere. Somehow I want to place these 2 A's. Right. So how can I select these 2 positions? We have these 4 options, and out of these 4 options, only 3 are available, mind you. These are the only 3 possibilities, because consecutively we cannot place the 2 A's. That is not possible. Right. So these are the only possibilities where how we can place either in the first and third, first and fourth, or second and fourth. So there are 3 ways to place these 2 A's. Right. And once I have fixed, so for A we have 3 possible ways, and for each such arrangement I'll have 4 positions vacant. So out of this 4 positions, 2 positions will be A. Let's say here and here I have A. I have how many positions vacant? 1, 2, 3 and 4. Right? So what will happen is, this first position, it can be filled in 3 ways, B, C, D. Then I have A. Then again this can be filled in 3 ways, B, C, D. Right? And again I have A, and then the final position, this position can also be filled in 3 ways. However, the last one can be filled in 2 ways, because if this position has one of B, C, D, I cannot have all three possibilities for the next position because consecutive passes are not allowed. So this will become 2. Right? So for this particular case, how many possibilities are there? 3 into 3 into 3 into 2. These are the possibilities. In fact, let me just scroll down and elaborate on the cases a little further. So with 2 A's, our cases are, we have 6 vacant positions, 4, 5, 6. If I put one A here and the other A here, this I can fill in 3 ways, B, C, D, multiplied with this I can fill with 3 A's. Remember, A and A are fixed, so this is basically 1. Like we have to multiply 1 because we are fixing A and A for now. Again, B, C, D. This also can be filled with 3 ways, B, C, D. Apologies for that. And finally, the last one, since previously it was one among B, C, D, it cannot be all 3. So we'll have 2 available at the last position. For example, here if it was B, we'll only have C and D available here. We won't have all B, C, D. That's what I meant. Now, so this is one of the possibilities. Of course, there are other possibilities. For example, if I place A here and the other A is here, this is also a possibility. So this can be filled in 3 ways. And this can be filled in 3 ways. This can be filled in 2 ways because one among B, C, D will be here. So repetition is not allowed. This can again be filled in 3 ways. So I have 3 into 3 into 3 into 2 once again. Finally, the last possibility, which is if I have the starting A in this position, the final A in this position, here I can fill it in 3 ways, B, C, D. Here it will be 2 ways because one among B, C, D will be in the first position. Here again it will have 3 ways. Here again it will be 3 ways. So overall, how many ways are there? 3 into 3 into 3, which is 27 into 2, 54. 54 each will come from these independent cases. Right? All these solutions are possible. Either this is a solution or this is a solution or this is a solution. Hence the total ways are added up, and hence for case number 1, the total number of possibilities is 162. This is one case which has 2 A's. Let's go for the second case, case 2, which has a single A in it. If we have a single A, again situation is the same. So let me draw a demarcation line over here just to separate. I hope this works. I'm creating a mess, but I guess that's okay. Now in second case, again we have the same situation, 3, 4, 5, 6 and a 8, and we need to place one A. So again in these 4 positions, I just need to select one position where I want to place my A. So let's just go through those cases as well. If I place A in the first position, this box I can fill it in 3 ways. This can be filled in 3 ways, and this can be filled in 2 ways because one among B, C, D will be here, and 2 ways, and again 2 ways because consecutively we have to place B, C, D. So this will be the number of ways if we place A in the first bracket. If we place A here, we have 3 ways multiplied with 2 ways, again 2 ways, and then again B, C, D will repeat. And same pattern will actually follow the other places as well. So if I have, let's say, A here, if I have A here, in the first 3 positions we'll have 3 ways, 2 ways, 2 ways because B, C, D starts repeating. Then again we have 3 ways here since there is A, and then we have 2 ways. And same will be the solution for the final one also. It just go through that arrangement also for the sake of completeness. So if I put A here, I'll have 3 into 2 into 2 into 2 BCD repetition and 3. So for every case I have 2 to the power 3, 3 to the power 2, which is 8 into 9, 72 ways. 72, 72, 72 and 72. Remember that for a particular arrangement, the cases within are multiplications because they are AND operations. So there are 3 ways, and for each of these 3 ways there are 3 ways and 2 ways, so on and so forth. And these are independent cases. So either this is possible or this is possible or this is possible, and hence these possibilities get added up. So for the second case with 1A, we have 72 into 4, which gives us, what is it, 280 to 88 cases. Now, we come to the last case, which is the case with no A present in it. So case 3, which is 0A. So if you have no A, that just simplifies matters a lot, because it's very easy to come to a conclusion. We have no A. So here I can fill it with B, C or D. But once I fill it with B, C or D, I have two options left, because one among B, C or D will be in the first position. Hence in the second position, I'll have only two options. So let's say in the first position I had a C, then in the second position I cannot have a C. Same passes are not allowed. So I'll just have access to B or D. And same follows there on. So here it's pretty straightforward. It's just 3 into 2 into 2, second position, third position, fourth position, and fifth position, and the sixth position. Because BCD, one among BCD will stay. So this gives us 2 to the power 5, 32, 32 into 3, 96. So these are the total possibilities, total possible arrangements with for all the cases. That is, either we have 1A or we have 2A, or we don't have any A at all. If we add that up, we get the total number of solutions. So this is this plus this plus this. So either it is a 2A case, or it is a 1A case, or it is a 0A case. Hence we add all the possible combinations and we get 288 plus 162. Let's see, that's 388, 448, 450, 450 plus 96. That gives us 546, is it? 450 plus, yeah, 546 possible arrangements, which is the correct answer for this particular problem. Just a quick recap what we did here. Oops, apologies. So this is the original problem. Consecutive passes to same person is not allowed. So the observation here was that there is a restriction on A. We cannot place A at x1 or x6. There are just 4 positions for A. And if we just pay attention to those 4 positions closely, we can conclude that at most we can have 2A in those 4 positions. We cannot have more than 2, because it will violate this particular rule. Now, if that is so, we basically have 3 cases. Either we can take 2 A's or 1 A or no A. And that's how we have broken down the problem. So if we have 2A, these are the possibilities. These are the 3 possibilities with 2A. And for each of the possibility, we saw what are the possible arrangements. How many ways are there to place BCD before and after A. And if there are consecutive cases of BCD, we can multiply with 2, because one of BCD is already there. And we considered all the cases for 2A. Similarly, for 1A, we had 4 cases. We considered all 4 cases. And similarly, for 0A, that is just 1 case which we consider. And all these can occur. We can say, all these are possible. So either this first case is possible, or the second case is possible, or the third case is possible. And within these cases also, either this is possible or the other one. So these are all additive in nature, and the total number of solutions comes out to be 546. Just a quick note on multiplication and addition, because I think it might be confusing to some people. Let me just take one quick example. So here, if I have 6 such positions, what I'm saying is, if I place a A here, what can it be? It can be B, C or D here. Here, it can be B, C or D, right? So I am multiplying, because when I have B here, I can have all 3 axes, B, C and D. It's not violating rule because there is a A in between. So BAB, BAC, BAD, all 3 are possible. Similarly, CAB, CAC, CAD, all 3 are possible. Similarly, DAB, DAC, DAD, all 3 are possible. Hence, we are taking 3 into 3. because it is occurring simultaneously. It is in a single case. For each three possibilities, we have three possibilities, and here we will have two possibilities. If we have a B here, we can have a C and D here. B, C, B, D, so on and so forth. That's why we are multiplying within a single case. Whereas for separate cases, it can occur independently. Either one case occurs or the other one occurs. That's why we can add them. So that's all for today's video. For the part 1 of the solution to this beautiful problem, this is how mathematically we can solve it. I hope at least some intuition has been built up regarding the solution to the problem, regarding the approach, what we are supposed to do. In the part 2 of the solution, we'll try to generalize it. We will not have a restriction on the number of passes like 7 passes. We'll have n number of passes, and we'll try to solve it for m number of players. We'll try to build a recurrence approach to this problem, and we'll solve it using an approach called bottom-up DP. But for this video, this is it, and we'll discuss more about this in the part 2 of the solution. See you there. Thank you for watching the video.